Okay, hi, welcome to the next lecture. In the previous video lecture, we talked about free undamped vibrations. Okay, so that was the focus of the previous lecture, and then spring or mass spring system, also called as harmonic oscillator, has been used as a model for free undamped vibrations. Has been used as a model to study free undamped vibration, and the reason for choosing that is that it contains core ideas of theory of vibration, which is an oscillatory motion about its equilibrium position. Okay, however so free undamped vibration misses a very important physical concept. Important physics. That is, if you plot total energy of the system with respect to time, so let us say total energy with respect to time, okay, for an undamped system, it remains constant. Okay, this is an undamped system, but in reality energy dissipation occurs, and with respect to time, without any forcing it, the magnitude reduces with respect to time. Okay, this is in reality. Okay, so in a real system, in the actual system, energy dissipation occur. Okay, this is mainly due to friction. Okay, and as a result, energy decays with time. So total energy of the system decays with time. Okay, this is what is going to happen in reality. Okay, so so that will be the focus of this lecture, in that we are going to talk about free damped vibration. Okay, so we are going to talk about free damped vibration in this lecture. Okay, that is what we are going to study in this lecture, and that is going to model the energy dissipation due to friction. Okay, so our goal, free damped vibration. So our goal is to understand what happens to a harmonic oscillator when we add friction. Okay, that is what we are going to discuss. Okay, so in particular we are interested in simplest kind of motion. Okay, in particular, okay, our interest is in the simplest kind of motion caused by ideal linear dashpot. Okay, so that is our interest. Okay, so we will find that the motion of the spring decays exponentially either with or without oscillations. Okay, so what we are going to find is that we will see that the oscillations decays, or oscillation is not the right word here, because oscillation may not occur. Okay, that the displacement of the spring decays exponentially with or without oscillations. Okay, that is what we are going to show by the end of this class. Okay, so before we move further, let us discuss about what a dashpot is. You have definitely heard this word. What exactly is a dashpot? Any idea? No? So dashpot is a tool that offers resistance to motion, by absorbing energy. Okay, so dashpot is any tool that offers resistance to motion by absorbing the energy from the system. Okay, and the main example, so one obvious example of dashpot is the suspension system of the automobile or in a bike. Suspension system in a bike or a car is a perfect example of a dashpot. Okay, so in general it has a piston cylinder arrangement. So you have a cylinder, okay, and you have piston with a small opening. Okay, and you have, okay, so that is a dashpot. So you have, this is the cylinder. No, it is the opposite way. So we have a piston and a cylinder, and within which you have some liquid. Okay, some liquid here. Okay, so that is the cylinder is filled by liquid, and you see that there is an opening here. Okay, so dashpot is nothing but piston cylinder arrangement in which the cylinder is filled with liquid. Okay, and the piston has a hole through which the liquid moves as the piston executes displacement. Okay, so there is an opening in the piston, so that when piston moves, the liquid displaces correspondingly. Okay, so the energy loss here is due to the viscosity of the liquid. So we say that when we say dashpot, we are talking about energy absorption, right? So here energy absorption Absorption happens due to viscosity of the liquid. Okay, so when the piston moves, the liquid has to displace, and this displacing liquid causes resistance to the motion of the piston and this viscous dissipation is what we mean here by absorption of energy. Okay, so in an ideal situation, you will see in the next course on fluid mechanics is that the resistance force offered by the dashpot is proportional to velocity. Okay, so let me say F is proportional to x dot, and we say F is equal to C x dot. Okay, so that is the expression for resistance offered by the dashpot. Okay, so where C is a parameter characterizing the dashpot design. For different designs of dashpot, the constant C can be different, okay, which is given by which defines the magnitude of resistance force. Okay, so let me ask you one question. I will not answer this question. You figure out. So we see that there is a hole in the piston when we have a liquid. Do we need this hole in the piston if it is filled with air or with some gas? Okay, so you think about it. Okay, think about it. All right, the hole is mandatory if you fill the piston with the cylinder with the liquid, but do we need this hole if it is filled with a gas? Okay, that is the question for you to think about. Okay, so now let us come to the main topic, which is the mass spring dashpot system. Is also called as damped harmonic oscillator. Okay, so we have a spring attached with a dashpot, and we have a mass attached to it. So the spring constant is K, the constant of dashpot is C, and this is M. Okay, so now the governing equation becomes mx double dot, which is the mass times acceleration, and the forces acting are now 2. This is the resistance offered by the dashpot plus force due to spring is 0. Okay, that is the governing equation of a mass spring dashpot system. Okay, if you observe this equation, the only design variable which is in our hand is the damping constant C. Okay, because mass for a given system, mass is decided by weight of the system. Okay, and spring defines the elasticity, as you know, which is a material property. Okay, so what do we mean by this is that, let us say you want to design a damper or you want to minimize the vibration characteristics of an automobile. The mass of the automobile is not in your control because that is fixed by several other design parameters, and the material that you manufacture your car is not also in your hand while you're controlling vibration. The only parameter that is available for you to adjust is the damping constancy. Okay, so how do we solve this system, this differential equation? Again, it has an exact solution that you know already. Okay, I'm going to write directly, refer to your ODE course for the details. So from this governing equation, the characteristic polynomial is given by m alpha square plus c alpha plus k is 0. Okay, so from here you can write alpha is minus c. You all know this formula, c square minus 4km by 2m, so that becomes minus c by 2m plus or minus c by 2m square minus k by m. Okay, so now there are three possibilities. There are three possibilities here. One, what do we call as critical damping. Okay, which means we have two equal alpha. So this is given by c by 2m square minus km equals to 0. To denote critical damping, we introduce one subscript here. Okay, this is c. Subscript c implies critical damping parameter. Okay, so this will give you alpha is so cc square is 4km. Okay, and the solution of the differential equation x of t is written by a plus b t e to the power alpha t. Okay, that is case one, which is we call it critical damping. Okay, the second possibility is under damping. Okay, which means that we have, for alpha we have complex conjugate pair of roots. Okay, so that means that c square, so the possibility to get complex conjugate for alpha is that c square by 2m square minus k by m should be less than 0. Okay, so that term should be less than 0. Okay, so what is the solution for, what is the exact solution in this case? Okay, so in this case the exact solution x of t is given by e to the power minus c by 2m times t a t plus dot t. Okay, so where lambda d is given by k by m minus c by 2m whole square. Okay, it's called as damped natural frequency. Okay, and the third possibility you might have guessed by now called over damp. Okay, which is given by C. Sorry, I have made a mistake here. Please correct it. There is no square here. Okay, so please correct this. I had an extra square here and I removed it. So here we have C by 2m square minus km is greater than 0, which implies C square is 4 km. Okay, now here the exact solution is given as a e power alpha 1t plus b e power alpha 2t. Okay, so if we plot visual picture of the oscillations, okay, so let us plot oscillation characteristics of damped harmonic oscillator. Okay, so we have x, okay, with respect to time t. Okay, so this is an underdamped system for an underdamped system. Okay, so the due to the damping, the magnitude of the amplitude of the oscillation reduces due to the energy dissipation, and x of t goes like this. Okay, so that is the underdamped system, and we see that, let us say that this is x n and this is x n plus 1, so the amplitude will keep on reducing, and the equation of this envelope is this is given by e to the power minus c by 2m times time. Okay, so the amplitude reduces exponentially. Okay, so here the characteristics here is that the oscillations reduce with respect to time, but at a much lower rate. Okay, so we have considered underdamped system. Let us now talk about overdamped and critical damped systems. Okay, so the critically damped system goes like this. There is no oscillations. There are no oscillations once you give some displacement to the mass in a spring mass system. Without performing any oscillations, it directly comes back to its equilibrium position. Okay, and then for this is this is critically damped. Okay, and for an overdamped system, it goes like this. Okay, so that is overdamped system. Okay, So the critical damped is most relevant for us because it implies fastest decay of amplitude and return to its equilibrium. Okay, so this is very important in design. Okay, then we have over damped system. This is represented by too much damping, which means that it takes a lot of time to come back to its equilibrium, and both of them are characterized by no oscillations. Okay, both critical damped and over damped system do not involve any oscillation. Okay, so mathematically critical damping the state of critical damping represents the transition between oscillatory and non-oscillatory response of the system. Three responses. Okay, so critical damping is like a kind of boundary that separates oscillatory and non-oscillatory responses. Okay, so now if we have oscillations in the system, how do we measure the damping? So measurement of so in underdamped systems, okay, the damping constant C can be obtained by measuring the rate of decay of unforced oscillations. Okay, can be obtained by measuring rate of decay of unforced oscillations. Okay, by unforced we are considering currently free vibration, so by unforced we mean there are no external forces acting on the system. Okay, so this is given by logarithmic decrement. Okay, given by d, which is natural logarithm of two consecutive amplitudes. Okay, so xn and x plus 1 are defined in this figure. You see that xn represent the peak amplitude of the cycle 1 and xn plus 1 represent the peak amplitude of next cycle. Okay, so that is given by e to the power minus c by 2m times time divided by e to the power minus c by 2m t plus the period of oscillations. Okay, so after some algebra you will get so this is minus c by 2m times t plus c by 2m t plus t. So the logarithmic decrement is given by c t by 2m. Okay, so by measuring the logarithmic decrement and period of oscillations. We can compute the damping constant C to be 2m d by t. Okay, so that is how we measure a damping constant of an under damped system. Okay, so we'll stop at this point. From the next lecture we will move on to forced vibrations. Thank you.